and to meet the future requirement, definitely you should be flexible enough. Now, these drives, in the context of drive, how can you increase the power? Let's say something comes up with a different feature that, I need a peppy drive or a sport mode drive, right? Now this power requirement is increasing. How do you do that? So this drive which is selected has a capability to, address your future requirement or not? Definitely. So this is what, few pointers which is required for requirement of drives and EV. Now, preconditions before drive selection. So, okay, so I think, just to tell you to the group that this is not just you can't select the drive without having certain preparation. And whatever I'm going to highlight here is required before the, drive selection. So let me talk about it. Is vehicle parameters. Definitely your vehicle selection, whatever you have done. So if it is a scooter or your bicycle or three-wheeler, definitely you need to have these vehicle parameters, that what part, what I'm going to. So this is nothing but a vehicle specification, that what my vehicle needs to do. So it is a, your final specification about the maximum speed and everything that's it is. And then from the drive perspective, what you need is that, hey, where I'm going to locate my motor, location of motor, right? So whether it should be when it is on the rear side in the differential, do I need to do that, or it could be part of your axle, or it could be in the front drive, right? Or you would like to have a, bigger shaft if you see in the trucks, whether you would like to put it on the engine compartment because of your space availability, whatever, right? So this topic itself, location of motor itself, is a very big topic where most of the OEMs take a lot of time in terms of deciding that which is the best suitable place for motor, right? And then, of course, that packaging, weight, overload conditions. I mean, this is required that, where is your other stuff available in terms of the weight target, because ultimately every vehicle has the dynamics, right? So, aerodynamic space and everything is there, but, you need to control on the center of gravity. So where it is mounted, does it, in the center, so that, while you take a turn or whatever, whether it is good or not, based on that the location is decided and the packaging requirements are crafted, right? And then it talks about how much is the weight available for your powertrain to, kind of put on the vehicle. Okay, then overloading condition. If you talk about auto rickshaw, in the countryside, we talk about three-seaters, but you will wonder that sometimes there are 10-15 people, right? So driving on the vehicle. And what is the typical overload? Because people used to, misuse or abuse the vehicle. In that situation, what is the real need, right? So we need to have those information, right? Environmental, is it going to go operate in the Kashmir area, or it is in the Delhi, or in the which region? So right, these temperature zones, geometric situation that, right, where it's going to operate. And I think in India condition, there is a wide variety of environmental temperature where we need to understand those. Second is the drive cycle. Now, as I mentioned, I think I given a background about the application, which application, your vehicle is supposed to work. We need to have this application first, and the different drive cycles related data. Third is about the vehicle configuration. Definitely hybrid or full electric is the choice that you will make to make the vehicle, but this is available, should be available before the drive selection. Then fourth is about the maximum speed, right? So again, this is part of the drive cycle itself, but, this is all important parameters from the drive selection. Hence I'm highlighting here that what's the maximum speed of the vehicle and how much time duration it needs to be there for maximum speed. Then again, maximum torque. Again, so this is your, the torque demand which is required. So at a maximum weight or a gradient, because, in the Indian context or everywhere in the world, there are different gradients which a vehicle needs to, drive. So this data is required. Maximum power, again, so I talked about your maximum power, your cruising, right? So maximum, minimum speed and maximum gradient, what the situation. This formally it is part of the drive cycles, but I'm just putting it separately just to highlight here in the group that these are important parameters which are a must for drive selection. Fifth is the battery voltage or a system voltage. Let me put it this way. So what is a voltage selection? Again, these are all architectural call. It's a vehicle architecture, and I'll tell you that this session itself, I mean, people take a lot of time in terms of deciding the system voltage. It is not a very simple game. Okay, so this is also required before the drive selection. Of course, the gearbox, which I said that it is motor plus your gearbox to drive the wheel, which is important. Definitely cost. Everything it is, the cost driven. If you can't fly, you build the vehicle, but you can't sell. So this is very important. Regulation at the end is definitely required because you can't fly the vehicle on road. Definitely, there are certain application which says that you don't need a regulation for a bike or scooters or certain kilowatt. But in general, you need to have a regulation compliance. So this 10 points is required as a precondition. Just want to take a pause and check with Dr. Vrushali. I think it's going good. Are you able to hear the conversation?
Yes, sir. Very clearly.
Okay, perfect. Perfect. Sounds good. All right. So I move on further. Right. So these are the variables. It is in the similar context what I said earlier, but I'm just going to take you this particular slide to define your specification. I think this is all right. So you look at this. Final output is what? These three variables I just put up here on the slide. The field variable, you need to have a drag, vehicle, drag, the gradient, acceleration, braking. All these inputs are required, and of course, you need to have a vehicle design related parameters. Okay, and the points which is highlighted in point number 2, and 3 is the voltage requirement, power system voltage, and source of characteristics, because of battery how it is behaving, from 100% SOC to 0% SOC, how it is behaving, you should have an input, of course, that is giving it to controller, and which is driving your motor, and so that is as an input, and you drive the motor and gear specification and controller specification. So at the end of the day, before you go and hunt for the drives and talk to your different suppliers, you should have the specification in front. So this is the process through which you will be able to craft the specification, right? So I think let's talk about types of drives. Okay, so there might be many different motors which are required. So I just kind of highlighted few five types of motors out here. There's first is induction motor, this is PMSM, axial flux motor, SRM, and BLDC. All right. So I think in this session I would not like to talk about these drives in detail. What I try to do here is just to give you a glimpse of it, because this each subject, each motor itself will take probably 1 hour discussion. But just to give you a gist of it, basically, if you look at induction motor again, so this is a pretty old technology which is used earlier in the industrial segment very well. It's a pretty robust and rugged. So you can just look at the picture that in the only difference when you put it in automotive, that is the vibrations. Okay, because the road vibrations, your bearing and other selection should be such a way that it can withstand it. Your housing in the industrial context, it might be different, but in the automotive context, it should be able to withstand. When it is running on the road, there could be a lot of you may have a ground clearance, but there are conditions where you can hit a lot of obstacles, right? And there are vibrations related stuff. So I think that's the only difference. But I'm just want to tell you that this induction motor is anyway there since ages. All right. But what's the advantage here? I think you can see is that of course it's a pretty simple in construction. It is a doesn't it's a low in maintenance, pretty rugged, and the lowest cost. Okay, because there's a lot of economy of scale perspective. This technology has been quite stabilized. Okay, and it is available with a different range of speed. All right, so you can look at it that can go to up to 25,000 RPM as well, right? What's a limitation here is, of course, there is a limitation in the starting torque, okay, as compared to other motor again. So it doesn't mean that it cannot put on the electric vehicles, but you need to look at your application and then market. Second is the power density. I mean, this is again a comparative. It is 2.5 kilowatt per kg. I mean, that's substantially good in couple of application, and it can take it up. But as compared to other motors, it is like 2.5 kilowatt per kg. Hence, it is tagged as a little low and lower efficiency. I mean, if you look at the induction machine, the maximum you can achieve till, I mean, if it is a good manufacturer, you can grab it till 92, 90 or 80s. I mean, typically on average, you will get about 88%, but good manufacturers with the cooling arrangement can go to 90 to 93. Second motor is the PMSM, this permanent magnet. Okay, so it has magnets, and these magnets are mounted on either on a surface of the surface or the interiors. If you look at the picture that itself, there are different magnets mounted. Now, this is an improvement on the induction machine. Basically, you with the more magnets, you would be able to get a more magnetism, right, which is between your stator and rotor, and whatever losses were there, you would be able to recover. So it is more efficient, and it brings a lot of advantage. What you see on the screen is, of course, it is a little more power density is a little more than the induction motor. It is 2.5 kilowatt per kg, but it gives you a good continuous torque, which was absent in the, I mean, which is little moderate in the induction machine, and it is higher efficiency. It can bring you up to like 94, 95%. And what's a limitation? I think let me highlight here is the limitation is about the magnetism. However, the magnets at a high temperature loses the magnetism, and but with the different changes in the magnets available in the market, this also has pretty better performance now, because I think it was evolved. Earlier there were a lot of disadvantages. All right, and very important is high cost because of the magnets, rare earth magnets. You put it on a motor, that's why the cost a little higher. So this is interior PM, permanent magnet. I mean, this is just to kind of show you the real life scenario. In the previous Toyota press, 2003 had, if you look at the slots on the lamination, okay, there are the dash. I mean, you see on the 2003 slide, right? So this is the how the magnet was there. In 2004, again they went to improvisation on the magnets in the V segment. Then in 2010, again they kind of had a dual magnets. It was internal magnets also, and externally on the surface, right? Ford has a similar concept about putting the magnets. Earlier it was used on the surface, now it is inside. That's why it is interior to the lamination. And likewise, you can see from Chevy, there are different magnetism. Now you see this, that whatever was there in the industrial segment, there are improvements in this construction, only because in the automotive segment, with the less space size, space constraints and higher efficiency, you try to improve the performance. So that's the trigger for having this kind of a magnetism, right? So this is Nissan Leaf. If you see on the right hand side, it has certain star related construction. So this is how, maybe I can highlight also. I think this is what Nissan Leaf, right? So this is how it is constructed. So the different, in short, these are different laminations and magnets which are mounted to improvise a torque, then your efficiency and overall performance of the motor. This is talking about the evolution of the magnets, right? So if you see that earlier the ferrites were used in 1940, then it evolved to aluminum nickel cobalt, right? So Nico, and then smarium cobalt, SMCO, which came somewhere in 1890s, and neodymium, which is 2000, and there are few more will come up. But I think the summing up is that if you look at the energy density on axis, if you see it is drastically increasing, right, on one axis, when it is so it is going about 480 now, and it is even getting more and more if there are more and more innovation going on this technology, and improvising the performance. All right, so this is what you can grab it as an overall view. Then Third is about axial flux motor. I think this is superior. If you see the axial, I mean here the rotor, then core, stator, then again rotor, then stator. So this is a combination. It creates, and it becomes so there are rotors and with the magnets and winding construction, bit of complexity, but it gives you also one of the flavor highly used nowadays in the high speed bikes. Okay. uh, you can see in the UK, you will see most of the super bikes comes up with this axial, which is kind of put up as a hub motor. So what's the advantage here is that, of course, pretty high efficiency. If you see 96% is pretty high efficiency, and you can have the very smaller battery pack to, because it is more higher efficiency, and then you will have better energy coefficient, right? So energy ratio is also better. Now it is a compact in size as compared to other motors. When you say compact is because it requires a little less space. If you see the higher power density, 6.7 kilowatt per kg, which is like 2.2 or greater than 2.2, it is like 3 times. And I have seen some motors which is like 12, ratio of 12. High power density is like 12, which is superior. And I think there is some technological development is also going on this area, which is making the motor smaller and smaller, so that you can house it in the applications, right? And pretty low in the weight, because at the power required, it's pretty small in size. That's why it is more compact. And again, a high speed range, 12,000. So definitely when you go with a high speed application, this can sustain there, right? So it is pretty good in that context. What's the limitation here? It's a high diameter. As I said, the axial flux has little more diameter too, because of the construction of the motor. Okay. And pretty good torque. At a high torque, it needs, if you have a high demand, then the shell becomes a little more in terms of diameter. Complexity in design, it is not so easy by any induction motor. Is pretty easy because the windings are, you can do it, but it needs a special tools to do the windings. And because you need to have consistent performance, it needs to be done through robotic related, all CNC operations, to kind of do this kind of windings and laminations and stacking the motor. So it is pretty complex in design, and high cost. Due to this reason, it is little more in cost. I again here, I have given a source of Yasa Motors, I mean, as a reference, which is giving a good equation. As I mentioned, the flux, see, look at this, it is 13.3 kilowatt per kg. Okay, so this is pretty good power density it gives, and which will be beneficial in terms of a compact in size. Then fourth is about your SRM. Okay, this goes up to, so if you look at the rotor has tooths which goes inside your stator, and this doesn't need a magnets actually, and hence but because of the construction, it gives you 94%. But only limitation here is that it has lower torque density. Okay. And the high ripple, because it gives a torque at a different frequencies, it gives a ripple, which gives you kind of a distortion, right? So this is a disadvantage. The fifth one is the BLDC motor, which is very famous. I think you almost be aware about this. The rotor has on the surface magnets, and the rotor rotates, right? And this gives a pretty high efficiency and power density, and with a pretty good head dissipation across the surrounding. I mean, it's a surface, it's pretty simple in construction. And what is the disadvantage? Again, it's because of Earth's magnets, it is, your it becomes a little expensive, and it gives also ripple torque at a due to back EMF. So this is what you probably need to understand. The control is a little complex, control due to controller, but I think these days BLDC controllers also has been matured to a greater level, so no need to kind of really worry on that front. This slide again is, I think, it just probably giving you a combined view. Maybe you can look at later, but just to see that pink portion here. Pink portion is, is kind of evolving over the years on the different parameters, right? On cooling, you will see that complexity. I think only PMSM has little medium, and axial needs a more cooling complexity because of the construction. And torque wise, all the motors are more or less at a high torque, and induction machine is little moderate. Power side, almost all motors are high except the induction machine. Torque ripple, induction machine wins over here. It's a simple construction, as well as the PMSM and axial, because of the ripple effect is not there. BLDC and SRM has. And noise vibrations, you'll see a moderate in induction machine, but BLDC as PMSM is pretty smoother, right? So this is how it brings advantage. Efficiency wise, you can see that typically axial flux motor wins over all. It is 96%, right, as against the other, right? And size and weight ratio is pretty compact except the induction machine, right? So I think and stacking wise, almost all it's a face to face or back to back construction. I mean, this is stacking is a process required for lamination stacking, and creating your motor construction for the stator rotor. And cost wise, it is induction machine wins over other. So this is there in the chart. So all right, so I just wanted to take another pause to check with Dr. Vrushali. Is going good? Just if I not lost everyone.
Sir, no problem.
Okay, great, fantastic. All right, so now this topic comes as the main, which is a step for selection. Now let me recap quickly. What we've seen so far is we looked at what are the preconditions required for any drive selection. Okay, you need to have your system architecture, your vehicle related parameters. Then you should be knowing about the different drive system which is available in the market. Okay, and you should know about drive is nothing but motor, gear, and controller. Okay, which is required for you to choose the right selection, right? And application, which is very important. We should have a specification through which you can derive the specification of the motor. All right. So now what you do, all right. So again, this is through these vehicle parameters. Okay, you would have the torque, speed, etc., which is the first thing which you would require. Second is the drive cycle. Third is the select motor. Now here, when you say select motor, after whatever based on the defined your specification, your QCD stands for, I think I should have elaborated here, quality, cost, and delivery targets, which is required to be mentioned. Then select gears, right? Then perform simulation. I think I would like to take a pause here. Perform simulation. Okay, very very important. Okay, because this is again not it's a simulated environment where you put it off all this drive cycles, whatever selected motor, your efficiency with the controller, you plot it on a graph to see that where do you stand, and then you should check whether it is giving a desired performance or not with the selected motor. If not, you go back to the step number 3, again check another motor with another gearbox, okay, and check again whether you need to have the desired performance. Because here what happens is typically the trade-off happens between your maximum speed, power, and the based on the selected application, the drive cycle. So this is an iterative on the simulation. Rather you go and put as a prototype on your vehicle and then try it out. I would recommend don't do that. Go for this 3, 4, 5 and tune it, and then go further. And then of course at the same time you should look at a packaging feasibility. As in the point number 1, it talks about location of motor. You should be checking whether you would be able to put your in the right place. And of course there would be a lot of clashes or whatever. You need to kind of remove that packaging related feasibility in the simulation environment, right? Then very important about the TCO, it is, I should have put up here, it is total cost of ownership. So definitely when you do this stuff, okay, it gives certain amount which is required to be spell out, right? Now at vehicle level, you have certain targets, cost targets, and you perform this back to your TCO model and see whether does it give you benefit, right? Because ultimately you are selling in the market, whether it gives you specific margins and other stuff, it is sellable. Not, then go back, because this is the specific stuff. It goes, as I mentioned in the motor selection, that there are some wins over cost, some wins over the performance. This trade-off is to be carved out like this, right? Because ultimately you have to run through this and see, you come back and forth and select what is important. Everybody wants to get, if somebody says that, hey, I want to select a motor, go for the best efficiency, but at what cost, right? So this kind of decisions you would be able to see, because sometimes the pricing also matters. Some, it is initial cost is high, or maybe operational cost is low. All of the decisions, put in the TCO to just check back whether it is worth taking that decision. Okay, then you go for TC, your prototype. And prototype, where you can really go and see whether it is giving desired result. Whatever simulation result it says, does it really give it on the ground? And then regulation check, right? So check compliance, because of motor controller, people will face a lot of issues in the EMI, as well as the right selections of the cables, sensors, and everything. And as a motor, there are also IS regulation. There are a bunch of regulatory needs that also needs to be compliant. So I think, this 9 steps, if you follow, then you would be able to uh, grab the right directions, whether your drives. And I'll tell you that, in past few years, okay, um, whatever I'm showing, it is a, kind of coming out of lot of experience. People go back and forth, and whatever I'm telling in, this, whatever, half an hour, 45 minutes, people have spent years to understand. And at the end, you get, you end up not choosing the right thing. And then sometimes it also happens that you go in the market and then you fail. See, this is market revert back to you, saying that, your product is not sellable, right? So I think this is the steps. Now I would like to talk about certain real life challenges which is there in as a selection of drives. Okay, so when I say that, I think I will look at a couple of places I mentioned that define drive cycle, right? So what is the drive cycle? First of all, people in the standard cycle, see, if you go for the regulatory needs, it will talk about the certain standard cycle, which is MIDC, or MIDC, on which you do on a test agency for certifying your vehicles. Okay, but in the reality, your application is different. So most of the time, people fail in terms of getting the right drive cycle, which is required. And of course, there are n number of methods to kind of grab the method to get the cycle. So let's say if you are putting your vehicle in the city, right? In the city condition, you need to really understand how the people are driving. There are different kind of drivers who drives it, right? Somebody is very aggressive, somebody is kind of putting it very lightly. And there are city traffic conditions, there are different terrains, gradients, right? All of this would be required as a practicality. One of the parameters, if you do not do properly, you will be definitely fail later. All right, so this is the typical challenge in terms of selecting application related and defining your drive cycles. Then second is about the efficiency of traction. Understand it. See, when you look at it, hey, my motor is giving 96% efficiency. Wow, it is good. Does it give on a ground? Is very important, right? So put it off that your drive cycles, plot it along with your motor efficiency, because motor torque speed characteristics, your efficiency curves, you need to put it on along with the drive cycles and see what is you are getting. Because every motor, of course, I think would be giving, they're different. And I think I would like to again portion here is that drive cycle matters. If it is a highway cycle where the maximum speed is there, if you look at on the left side here, okay, so this is basically your the speed is on the high side, and the performance of the motor would be different than the other portion. So what is the application where you are putting your your motor, and what is the traction efficiency comes up. So you need to kind of understand this, and then take actions to kind of bring it back on the efficiency zone, which will be beneficial to you, right? And the third is about the traction performance. Okay, I think I mentioned about this, but these are the few pointers that there are combination of gradient. Okay, the gradient, whether it is if it is in the hilly area, the gradient performance is different than in a city area. You should understand that environmental conditions to be laid down properly. This is required to be fed for the simulation models. Full load conditions, variation in the system voltage, which you need to understand. Your performance of the battery pack, is it consistent, right? I think Mr. Sheldon or earlier session must have happened. How the battery behaves? Does it give you the same sort of power or a current demand from 100% SOC to 0% SOC? You need to understand where, and hence most of these test agencies also has the battery simulator that actually simulates the real life conditions of the battery pack to understand the performance of the drive, right? So this is important, and I think very important, I think, which was the earlier session about the motor coolant. Okay, what you are considering the proportion of what is this water, your glycol. These decisions are pretty important. Maybe it is covered in the thermal simulation, thermal sessions, but this is what pretty important. So with this, I think I would like to end this session, and I would like to open. Of course, it is 12:55. I would like to kind of ask for the question answer before I go to the next session. So just want to check with Dr. Vrushali. Um, I mean, I hope like it is you are following this session. Just want to again check back and then open up for the question answer.
Yes, sir. It is very clear, and we'll check for it.
I mean,
Uh,
if it is, if people wants, oh, okay, people cannot speak, right?
no,
I
they
need to
can
read out.
speak. They can speak, sir. But normally, after covering entire session,
Yeah.
we give the time to them. So
Oh, okay, okay. So should I go for the next one?
yeah, yeah. Whatever is
All
your
right,
remaining topic, you can cover it, and then we'll give
all
them
right, all right, all right.
15,
Okay.
20 minutes for it.
Because both the topics are pretty heavy. When you talk about an
Yes.
electric vehicle, the battery and the powertrain, that's the something which is going to drive everything, because one is the energy source and another is the powertrain. Anyway, I think I'll just go through that the second session, and then open up. Well, I think I got little probably late, so I think it is 12:55. I wanted to keep like 15 minutes for that, but anyway, let me go. Uh, so you can see my screen, right?
Sir, are you comfortable with whatever this topic on this people should ask the questions? Are you comfortable for that? Then
Yeah,
I
I'm good. Actually, I'm good. But if I mean, I'm okay to continue second session also. But I think I'm flexible. Whatever you feel so.
okay. All the participants, as these two parts are of different aspects, so I would request to all that if you have any questions on this covered topic, you can ask. You can put the message in the chat box also. Anybody is having any type of question?
Or if they may not have prepared, but then what I would do is maybe they can park it along with battery pack. If they want to combine together, I'm okay. Maybe I can go ahead. I can't see any questions so far in the chat window. Um,
Yes, okay, sir. Then we can continue.
all right. Okay. Oh, I could see certain messages. Okay. So please select hide option that I did later. All right. Okay, so just wanted to check whether you see my screen now.
Yes, sir.
Okay, great. Right. So I think no hide bar. Okay. All right. So second topic is about the selection of battery. All right. So let me just go on this. What I'm going to cover is, first of all, what is battery? Okay. And what are the different application of the electric vehicle, which is probably I covered earlier, but I would like to substantiate some example. Then third is about requirement of batteries for EV. Preconditions before battery selection is the fourth. Generate battery specification, typical specification, how it looks like, different types of battery chemistry, future trends of EV battery, selection criteria, which is what the topic is about, battery, and then challenges while selecting the batteries. All right. So now I'll go. I mean, I'll skip this part which was there just to set a background because these are two different presentations. All right. So what is a battery? Now, I think when I pose this question, most of the people will say that, hey, look, battery is the energy source. It has a cathode, it has anode, there is a separator, there is a electrons flows between, right, all of stuff, right, all this kind of uh, definitions. But I think, let me tell you that what is battery? Do you see this? What is battery here? Battery is a fuel tank, equivalent to fuel tank. Why I'm telling you this? Okay, and I'll tell you that in most of the session in the international conference, I also shared this, is that look at from the user perspective. Now, this particular session or context is not about the chemistry related discussion. It is more from the high level view where you would like to understand this battery is what in the conventional. See, people are, you look at it that people are leaving their existing conventional vehicles and switching back to electric vehicles. Why? In that context, this battery is a fuel tank. So, it is whatever you charge, it will give you a range. Whatever you fuel inside the conventional vehicle, it will give you the kilometers, right? So, I think this is what the conventional model says, and this is what your electric vehicle says. Okay. I mean, I wanted to kind of give you this thought, and I think you'll understand more in the practical world that why today people are really facing problems in selecting the EVs because of the range anxiety, and there are issues on the range, right? So specifically, this is what I want to tell you is the battery. Now again, this I already substantiated in the last presentation also. This is two-wheeler, this is three-wheeler, this is four-wheeler. Only difference is in this quick charge. If you look at this particular application here, I just change it little bit, the quick charge, because if you look at, this is a pantograph which is charging the bus, okay, just like a railway. And in this battery context, I change this picture just to tell you that, hey, look, this is charging the bus with the fast charging in the big buses, because it's a pretty big one, big batteries, in just 15 minutes or 20 minutes. And what kind of application is this? And hence I little change this picture just to tell you to this forum that, please understand, there are n number of application where this is a specific thing which in the context of battery selection, we need to understand this context also. All right. So let's look at what is the requirement of batteries for EV. Okay. Definitely, it should satisfy your range requirement, long life, consistent performance. Very good. I mean, this is required. Every battery which you put on your vehicle should give you the end of life. Well, very good, fantastic, right? This is everybody wishes to get lightweight and high power ratio to power to weight ratio. Definitely, it should be very lighter, right, and give you better power. Provide consistent current during high torque requirement during starting and climbing. Definitely, when it is when the motor is pulling the vehicle, it is getting the current from the battery source, and hence starting or a climbing situation definitely need consistent current irrespective of the situation of the battery pack, right? Then provide consistent power. I think this is also there in the drives, and whatever there was a drive, definitely it is required back to back as a battery. The battery is providing those supplying the demand of the powertrain. easy replacement of the faulty cells, right? Now this is in terms of so once you understand that it is not just you put the battery on a vehicle and then relax, right? You need to also understand about why the replacement happens, what do you need, because for the consumer, okay, customers would say that, "Hey, I need a list." If you look at in the conventional vehicle, does it talk about any change in the fuel tank? Okay, that's the difference between coming in here in this mindset of the consumer. Okay, that's what I'm producing here, that this is what is also required. What is, how do you replace, also needs to be as a requirement comes. Scalability of battery pack, definitely, as I mentioned last time also, that what you define your battery system as it should be across the vehicle platform. And definitely economy of scale plays a vital role, and flexibility in adapting future requirement. Today it is this range, tomorrow it is more range, whether it is your battery agnostic system. Okay, tomorrow this battery chemistry is not available, there is another one. Do you is it easy to adapt to the new system? Are you flexible? These are definitely required for the battery systems. All right, now I'll go the similar way what I have mentioned for the selection of the battery selection for the drive. There are a lot of commonalities. Okay, vehicle parameter is important, definitely it talks about, but you look at this particular thing from the battery concept, battery context. Okay, again, location of pack is important, whether it is in chassis or it is on backside, it is on the top of the battery, very very top of the roof, where the CG is going to matter, right? It can topple the bus if it is not distributed properly. And also so that kind of stuff is very very important. You have to do the vehicle simulation, and hence I'm putting this thoughts here. Or near to the drivetrain, it cannot go on the top of the roof. So look at this part, environmental condition, very important from the battery. I think earlier maybe many sessions must have happened. Okay, Mr. Sheldon, or right now earlier session also it must have emphasized this is important. Again, drive cycles, I'll not put more time on this. Vehicle configuration is common. System architecture. Again, for this fourth point, people take little months to define the system architecture in terms of what is your defined system voltage. Whether it is battery agnostic, which I mentioned, that you system architecture such a way that tomorrow it goes with your another battery chemistry. Are you able to do it easily or not? The system architecture takes this kind of decision and needs to be ready before battery selection. Regulation needs safety standards. I think someone must have mentioned about cell penetration tests. There are a bunch of tests for the standards. You need to know about what is your my safety standard define, and whether I should be able to tackle with that, right? So I should know about the battery compliance to this battery parameters comes from the system architecture, that hey, like, no, your battery pack should give me this much power requirement, this is energy, this voltage, this is life requirement, obsolescence. If I select some cells which is going to obsolete, and if not available, can I do it? Because when you say that my vehicle today is going to run for 10 to 12 years, right? If it is obsolete after 6 years, then what you are going to serve your customer? You need to have those thoughts while you are selecting the battery itself, and you should have answer before you go ahead. So this is a system level requirement, where you need to have this kind of stuff ready. Charging requirement, definitely you need to have fast or slow charging. Swapping options are also prevailing in the market. You should know about it. How, if this comes out, are you ready with that or not? Cost, I mean, definitely cost plays a part in the TCO, and there are subsidies. I think earlier session we talked about FAME2, what it talks about it, how do you claim, how do you grab this, and etc. So you should know about this as a handy. Now let's look at it. This is the specific stuff which comes out of your that exercise when you preconditions. That this is, I mean, this is just a example. This is not talking about any specific application, but this is what you need to derive the different chemistries. Okay, we'll come to that point in the subsequent slide. But what is your kilowatt hour pack requirement? What is the energy density? What's the rated voltage comes out here? If it is a pretty bulky, where I talked about the pantograph bus, where it can go to 1000 volt also. right? It and why it requires because of and then your current requirement becomes for the same power. The current requirement becomes lesser, and you will not incur losses in having the big thick cables and other stuff, right? So this all system architecture driven calls, but you need to kind of derive out of that, and then this should be ready. What is the range requirement? What is the temperature requirement? This becomes environmental conditions you would know about, and this also will talk about the storage, right? Storage again, it comes from the chemistry related, but again that needs to be jot down here. Liquid cooled or cooling system also need to be done, like cycle life, how much you are expecting based on your TCO, that needs to be kind of fulfilled. Then weight requirement coming from the vehicle packaging perspective. So what I'm trying to say here is that this is the specification come as a high level from the earlier slide. After finishing those 10 points, you would be able to grab this battery specification. Now I'll jump on this things. It may be repetitive, I'm not sure in the other sessions, so I will not spend much of a time because this is known. But I think just fundamentally, if it is not covered earlier, I mean, this is how the evolution happened. Lead acid battery, okay, nickel cadmium, nickel metal hydride, okay, which was the earlier chemistries, right? And lithium ion is evolved, which is giving a good specific energy and specific power, right? So if you see on the chart, it is pretty good, coming on and on and on, and that is changing over the period of time. So what you see on the right side, this all chemistries are lithium ion, and lithium ion is the highest, has a highest specific energy density, watt hour per kg, as compared to these three: lead acid, nickel cadmium, and NiMH. All right. So I'll just quickly go over. I mean, will not spend much of a time, just to give you some tips about it, that what kind of lithium chemistry is available. So look at this LMO. Okay, I'll just go that LMO. I think you can. I think it is mentioned in the earlier session also, that this is lithium manganese oxide. I think I was hearing maybe 5 minutes some questions also, so I can grab it. That this is, I believe it is there. I don't want to repeat again. But I think you look at this important stuff is the voltage. Now, when you look at the specification which I mentioned earlier, this is one cell is like 3.7 volt if it is LMO, wherein if you go to the LTO, it is 2.4 volt. Now, what I'm trying to say is that to meet your voltage level requirement, you would have all series parallel combinations, all modular architecture to kind of create to that level, so that it goes into high voltage, and you would be able to kind of give it to your controller, so that controller through it will be operate your motor, right? So this is how I look at it. So I'm saying that we need to understand what kind of chemistries will give what kind of different voltage and ampere hour requirement. Okay. Then specific energy, which is pretty important for any vehicles to be made, that how much kilowatt hour per kg that you would like to incur. Definitely everybody wants to go for the highest one, but again, you need to look at the trade-off analysis, that the you can't really go. Let's say, look at here, the specific energies NCA is pretty good, right? But it has certain other disadvantage, where while you do the simulation, I'll explain that it will have these iterations will come in the simulation, then you will choose the right stuff. Okay. Then this is important: charging rate. Definitely, everybody wants to charge it as fast as possible, the fastest. But then what's the limitation on the chemistry? Okay. So this is each cells would have behave differently. LTO gives a pretty good advantage over others in terms of taking the high C rates. Okay. Discharge rate, if you look at, is here LTO has a 10C possible, and somewhere in LFP is pretty also good and safer, that some cells can give 25C also. But again, I think we need to look at those selections of requirement. When the discharge C rate, if it is higher, you would be able to use it pretty good as a power. So these are power cells and energy cells. Some power cells would be able to give that high demand, it will satisfy, right? So again, this is all manufacturer provides this, and needs to be look at it. Cycle life plays a vital role. I think 3000. So highest is the LTO which provides it, but there are some disadvantage in the LTO cell also. In the specific, if you look at the specific energy, is just 70-80. cycle life is good. If you go for 80 watt hour per kilometer kg, then it's pretty bulky, and it gives you advantage of fast charging, discharging, good cycle, but then your specific energy is pretty less. So again, I'm saying that these all application, if it is a bulky vehicle where you can accommodate this, your vehicle engineering, you would be able to select this. Otherwise, you have to go for some different cells, right? So this is your thermal runaway, which I think Mr. Kapil said in the earlier session about the different temperatures that is available. And I think Mr. Sheldon also talked about it, that BMS, how it helps to, supervise all this stuff, right? So I think this is needs to be understood in thoroughly, and different combinations would arise out of this. Okay, so this future trend, I mean, I would not like to talk much about it. Is going to come. This is all futuristic stuff, but just want to tell you that lithium air, which is gives a pretty good. If you look at 13,000 watt hour, okay, it's pretty good. Where watt hour per kilometer is coming up, and why I'm sharing this is basically while the selection, uh, typically people will go for, oh, this is what is available, but in the future, what is going to be there? If you are aware, then your design, you would be able to make it such a way that it can adapt, or you'll be flexible enough to adapt it, right? So that was the reason why I wanted to put this slide on. So voltage ranges also varies. If you look back, the earlier selected chemistry versus this, there are variations. Specific energy density is the highest in lithium air. Of one, charging is unknown right now, which is what people are working on it. But this is some of the stuff is like solid state, which is very promising now. It's 300 watt hour per kg is going good. Lithium sulfur is also like 500 watt hour per kg, and it can take again. So it's a point to see. It's pretty less as compared to the solid state. It's got a rapid charging, and discharging, it talks about certain comparison that lithium air is low power, inferior, and this is solid state has a poor conductivity when cold, but otherwise it gives you a good discharging capabilities. Okay, on the safety terms, I think more or less some of the chemistry stacks need improvement. It is more to do with the gases which is formed, and the temperature related limitations. But if you work out well on through the BMS or your cooling mechanisms, and create a structure such that the gases which are created can be vent out, I think it can be worked out. Okay, so this needs improvement. Doesn't mean that it cannot be utilized, but people are working in the R&D for making it happen. And this talks about the failure mode, which I talked about, what really happens. Okay, so these are disadvantage right now in these chemistries, right? I'll not go much in detail, but you can probably read out that later. Application is where this can be used. Okay, solid state is going to be, in whatever I hear out, the solid state is going to be very promising, and there are a lot of talks going around about the future in EV. Okay, and that's all. I just want to take a pause, just check with Dr. Rushali. Is it fine? Is going good? You are
Yes, sir.
able to hear?
Yes, sir.
Okay,
It
great.
is.
Okay, great. All right. Uh, about the cost projection, I think these slides are already there, and many of you must be aware. I think it's dropping down with the different chemistries, additions of metals and everything. And I think, I'm not sure this is produced earlier also, but what you see on the graph is falling down, and this is what the reason why it is said that in 2030, I think it is going to be a very different scene. Okay, people will prefer to go for the electric vehicles, and because of this cost projections which are there, in 2030 it is going to be pretty less. And I think about Tesla's comeback in India, talking about their vision about putting this cost to a level where it is quite affordable, and it will be uh, used in most of the electric vehicles, right? So I think so this is which is talking about, I think I'll skip out this slide. Is also repetitive, but I wanted to highlight only this solid state. which is there. I mean, this is going to be pretty good. I think other chemistries I already talked about it, that how the specific power to specific energy ratios are. So I will not repeat again. Now, let me come back to the form factors. I think I'm not sure whether this is covered earlier, but there are three types of construction. One is prismatic, another is your cylindrical, and your pouch. Now, like look at it that this is your one cell. Okay, in the prismatic, you put it in the form so that you can create a battery pack, and it gives you. In the cylindrical, you look at this. This is 21700. There are different construction, 18650, and Tesla has now moved to 46, right? So so when you pick up this cell, okay, a tiny cell that you see, and then put it up on this box, and then you create this complete battery pack. You put a BMS, which I think Mr. Sheldon must have explained how these cells are monitored, right? So this is a second form of lithium ion. You can put a battery form factor, and then pouch also gives you. So this is just to tell you that how the construction happens. And okay, now let's come back to this point where we the selection of battery. Okay, so I think let me revise once again that we created the specification earlier after the selection of understanding the application, and then we create the battery specs specification, what you need, and then you look at on the this diagram. Okay, this spider chart, what you see, it gives you a holistic view of how these different chemistries are playing. And I think this is more this slide is it's kind of available across. I thought to put it up just to kind of give you a view. Look at this LTO. Let's look at it now. The C rates is for gives you fast charging. It's pretty good. So yellow line is LTO. LTO gives you more advantage on the C rate, wherein if you see other chemistries holds almost at the same place. Okay, then if you look at the thermal stability, the withstanding capacity in the ambient high ambient temperature, it is pretty good, like in Indian context. And LTO and LFP is the is pretty good. I think most of the OEMs are coming with this kind of chemistry. LTO being a little costlier, people feels to go for the LFP cells, and other cells are also there, NCA, NMC, and other. It is also picked up in some of the cases in Indian context also, and outside, and because of other trade-off. Okay, because thermal stability you can handle through your thermal management. I think this is what Mr. Kapil addressed in the earlier session. Specific power, definitely everybody needs a pepid ride. Okay, the super bikes application example. So there you will be able to put your NCA cells, and it's all application driven. And LTO has kind of it's come down there a little bit as compared to other. Energy is, as I mentioned about the eco ride, where you need a better range, higher range. There you can go for this kind of cells, and NCA wins on the priority. So that's one point. And safety, again, role of BMS is critical here. I think if we look at the earlier chemistry also, wherein you can allow, you can prevent these batteries to go on beyond the critical zone. Definitely, you would be able to operate in a safer zone. Some of the chemistry cells, if you go deep discharge, it will be a pretty bad in terms of safety as well as the life cycle, right? So I think you need to understand, and those gives you better advantage, which you see on the screen. LFP LTO wins on the other cells. Performance wise, definitely I think you look at charge discharge balancing, etc. If you look at the LTO is better, LFP better, and then the other chemistry comes. So performance wise, you can see what's the advantage. Life of the battery, definitely LTO, as I mentioned earlier in the graph also, is pretty good as compared to other. Cost of the battery, I mean, if you look at LFP and other cells are pretty good, but this is general guideline. Whatever you see here is general. I think there are certain things which also play a role of the economy of scale, then the equation might be different. So, this is just giving a snapshot that, while you want to take a decision, typically what is the situation across the different chemistry. And I think this needs to do a spider chart sort of analysis in the coming a few future technologies, battery also. So that what's there, what's going on there on the in this different parameters. Just checking with Dr. Rushali. I hope like you're able to hear.
Yes, sir.
Okay, fantastic. Now, now this is what is talking about the selection of battery cells. Okay, battery cells for the pack. And here again, it's a similar thing which I mentioned. I think air condition is the new things, because most of the vehicles also coming with the commercial or this, air conditioning needs, and the apart from the traction needs, air condition is also needs to be satisfied by the vehicle, and that is added here. Charging infrastructure, definitely, what kind of infrastructure is there. Again, here also, just to tell you that there are different standards from the charging. Of course, in Indian context, there are AIS 138, which talks about three things, which is CCS2, CHAdeMO, and GBT, of course. But in the FAME context, GBT is not there. Other two standards are there. But why this is important, that you should, I mean, this is part of your BMS, but still you should be knowing about how your charging infrastructure, because it's going to be common, and it's a standard which is driven. Today, people go for some of the proprietary needs, that is going to be hindrance later. So this also needs to be there in your mind for the charging infrastructure and looking at the battery pack and BMS. Definitely driving cycles, I will not spend time here. Select cell. Okay. So define, I think you in the earlier slide you saw that define specification, select as per QCD. So quality, cost, and your performance delivery targets. You select a cell, then battery, create a battery pack, and using and the BMS. So you need to perform the trade-off on the different cell package options. Whatever you select, then you would be able to understand that how your equation becomes on the pack side, because is it becoming bulkier. I mean, this is all on the paper calculation first of all, and computer system compute the voltage of the system, because you have to connect certain cells in series and parallel, and whether it needs your system requirement, which you have defined. Example, if it's 1000 volt, this needs to be looked at around, and select BMS again. So BMS should be such a way that it should be battery agnostic in irrespective of the chemistries. You should be able to parameterize it so that you can compute the SOC, SOH, and bunch of other parameters, your fault tolerance and other stuff. So that BMS plays a vital role, which we can support the other chemistries. Then perform simulation again. So this simulation would be required, and there are a bunch of simulation software is available that you can use it, and with the different capacity, you would be able to kind of grab how the battery pack is behaving, and whether it is giving desired performance. So this would be iterative, because I'll tell you that this is more to do with your vehicle system, and you would be able to grab the real performance requirement you can qualify. Then packaging, you need to do a packaging feasibility in the context of the vehicle. TCO, I think, is mentioned. Prototype, you need to do desired result check regulation. So I think more or less whatever I mentioned for the drive also, it is similar to that in battery pack, but barring certain other parameters. But I'll tell you that interesting part is, um, you know, um, your see this motor system, which is kind of selected. Um, if that simulation works out well, then your demand is supplied by the battery pack, right? So it is all dependent, and hence I kind of was putting on this as an interface about the specification needs, so that in the bigger organization there are different departments works, and there are typical challenges comes during about the it's because it is, you can see this more evolving exercise, and if there is any specification changes, your entire iteration change. And if that's the reason, this is to be, I would prefer to go on the simulation first and then you go for the prototype development. Otherwise, it in the on the vehicle, it will be a lot of iterations and a lot of prototypes that you create, and you may or may not get the results, right? So this is what I want to give you insight about this. Now, the typical challenges which is coming out from my experience is the selection of cells from the TCO perspective. Okay, so very very important is the life and the replacement cost. I mean, I'm talking about the replacement cost. Typically, is pretty important. The TCO model should be able to address a lot of parameters, and there you should be able to compute what is the total cost of ownership. Otherwise, you will fail later. And here, I just wanted to emphasize is that you should also look at the obsolescence and the probably you can look at the train of the battery which is going getting slashed out on the pricing, how it is done. It is not a very simple exercise, let me tell you. This requires a lot of efforts to kind of build this TCO model. And I think a lot of people industries are still evolving on this and incurring losses, or maybe I would say that uh, it comes as a surprise rather, because it has not been done on a paper way. So I think these are the bunch of things need to be put up in the models, okay, so that it becomes more better results in terms of selection. And I think I talked about the fast evolving battery chemistry, obsolescence, right? So cylindrical, as I mentioned, that it is changing a little faster. If you are incurring lot of cost on the battery pack in terms of your design, about accommodating 18650 cell example, let's say you are putting a lot of amount of money on the dies, on tooling, etc., you should be very cautious about it, right? Or you should be looking at number of parameters, number of kind of a dependency with the suppliers and supplying this to ensure that you will be able to still continue with that for the tenure of the life of the vehicle, right? Because it's 10 to 12 years, and look at this is pretty changing very fast. So this is a bigger challenge that we see in terms of making it working on the ground, right? Similarly, prismatic also. I mean, prismatic is just an example. There is a pouch cell also, but I think please take care of this point well, right? Now, second point is about manufacturing of the battery pack. Again, so you might feel that we don't make a manufacturing of we don't make the pack. It is could be done by the supplier, but I think look at that. These problems are associated with the supplier also, because he is going to work with you continuously. So you should understand this, that the manufacturing process should be such way. It is what happens is that cell to cell variation comes, and and there are difference in the characteristics observed in the manufacturing process itself. Because this, I think, I'm not sure I got a chance to look at the cell manufacturing process, and I think uh, there should be one session. I would suggest that cell sorting and characteristics while it manufactured, you should understand that well. I mean, that is required as the precondition for the battery pack, right? So you would see a lot of differences between cell to cell, and it needs to be if you don't kind of do a cell sorting process, it will end up into a good amount of time in the balancing of the battery, and that will be kind of a very erroneous kind of way to construct your pack. Okay, and there's a high impact on the charging time in vehicle, so it will lead to a lot of problems later, right? So this is one of the challenges that and solution I'm just suggesting here. And the selection of welding process, I'm not sure whether anybody talked about the fusible bus bars, and so there is a concept coming in to protect your cells. Now you see that you looked at a different forms of battery pack, right? If you go for the cylindrical one, there are thousands of cells comes in the battery pack, right? So if you put, have the protection for the fuses for each cells, it's pretty complex. But apart from that, how do you put the fuses on the for the particular cells? Okay, and that is what kind of welding you use to kind of do this. And that is, I mean, I'm just giving you a little detail into this. That is pretty important. This ultrasonic welding over a spot welding calls to be taken, because that gives you a different resistance path, and it gives you different equations, right? Different results. Though you have selected the cells well, and but it eventually gives you a different result. Now, second is about the during the replacement. Now, see, you would construct the pack and kind of deliver along with the vehicle, and during replacement, you should not have a difficulties in to replace the cell level, right? So you can look at that. I think if you look at today also, there are vehicles like Hyundai Kona, right? MG Hector. Okay, people are giving different solutions, because if a user comes up and say that, hey, look, after 6 years, I need to spend what amount? Okay, in operation cost, I'll save a lot of money, but end of the 3 years or 5 years, as for the life of the battery, if I have to spend again 3 lakh or 5 lakh, definitely I kind of lose my money, right? So what is the solution available? And this also depends on this kind of a solution, that in the replacement, whether you would be able to replace a cell level or a pack level or a module level. This is very important. Okay, that is a very different challenges. Okay, this is a point number two. Point number three is about the packaging of battery pack. Okay, which is, I think, earlier session must have addressed about the cooling requirement. This is packaging challenges. Okay, I'll tell you this. The packaging of cell itself is a pretty different designs, and lot of times invested in the how do you construct the battery pack filled with the different combinations of battery cells. Example, if it is a cylindrical cell, there are n number of places, you can put in series or sequentially. You can have a honeycomb design. You can have, see, there are n number of designs coming in terms of your cooling requirement, as well as your your packaging, so that you can pack it in a smaller form factor, right? So this is important in terms of this is another challenge which is required to be faced. And the fourth is estimation of the life of the battery. And I think this is what in earlier sessions must have talked about it, that most of the manufacturer claims life. I mean, if you look at any, there are most of the suppliers from China, but you talk about certain life at the temperature,
Hi.
and this is a function of temperature. Sorry, who is there?
Uh,
There is somebody speaking. Okay, all right.
All of you are requested to switch off your mic. Virulkar sir, Virulkar sir, please switch off your mic.
Okay, all right. Thank you. Right. So I think life is still kind of a lot of people put a lot of money in terms of estimating the life of the battery. There are, of course, the cyclers and cell cyclers or pack cyclers, but it is when you anticipate a life of 8 years, definitely still there is no standard equation kind of confined which can give you. This is another big challenge in terms of selection of battery. But let me tell you something is that when the cell manufacturer says something and the reality, there are a lot of differences. Okay, and that is something, it will change your equation dramatically. So this is what I would like to highlight. In life at cell level is different, which is what I mentioned about it. And that's all about this. Now I would like to uh, now open up for the questions. One second. Okay, let me go back to this. And okay, now